In this section, we're going to talk about recursion and recurrence relations, and we'll see how recursion is used as a word as we look at some examples. So it's often the case that when we're talking about an integer quantity, or especially non-negative integer or positive integer quantity, if we want to define something that is a function of n, it may actually involve building that up from earlier values until the value we want. So in a sense, that's what recursion deals with. But we're going to do this by looking at a calculation of a to the n, where we're given a number a and a non-negative integer, say n. We're going to think about how we actually do this. And as we talked about this in class, the idea is that if you're going to really multiply n factors of a, you're really going to do this by, first of all, multiplying 2, and then multiplying that by a third, and so forth. So for example, if we wanted to calculate 15 to the 7th power, we might first of all calculate 15 squared, and then 15 times 15 squared to get 15 cubed, etc., like so. And in fact, in practice, in actual practice, that's how this would be done, even if done by a computer. And so we're going to give a formal definition of this, a recursive definition, by saying, first of all, a to the 0 will be defined by, and I'm going to use that colon equal for defined by to be 1, and then recursively, a to the n is gotten from a to the n minus 1 by multiplying a times a to the n minus 1. And so this would be for n greater than or equal to 1. So that's a recursive definition. That's a multiplication symbol. And we can do the same for n factorial. Again, this is the way a computer would implement it. And in fact, it's really the way you would be thinking of it too if you think about how you actually do it. You don't multiply all the first n positive integers together all at once. You do it step by step. And so our definition would be 0 factorial we define to be 1, and then subsequently n factorial is defined to be n times n minus 1 factorial for n greater than or equal to 1. Those are recursive definitions, so a particular definition is, or a particular value is given in terms of the previous ones. Sums are similar. If you gave a computer a string of numbers and asked for the sum of the first n, it would do it by first adding 2 of them and then the third one to it, and so forth. So we could define the sum, I'm using s for sum, sub 0 to be 0. We've added nothing there. And then subsequent sums, s sub n, would be the sum of the first n minus 1 of them plus the nth one. So this is intended to be, this s sub n is intended to be exactly that right there. So those are recursive definitions. Now this leads us into the idea of a recurrence relation, which is similar in the sense that we're going to create a sequence by means of an expression or recurrence relation that tells us how to get one term from the previous terms. So this is the Fibonacci sequence, but first of all, just let me mention the notion of sequence. A sequence is just a list of terms which typically will be infinite. It goes on forever. People do talk about finite sequences, but we're going to focus our attention on a sequence that is potentially infinite in terms of the number of terms it has in it. So it's just a list that is subscripted by the positive integers, or sometimes by the non-negative integers. So it could start A1, A2, etc. like so. Could start with A0. In fact, that's often true. But for now, for the Fibonacci one, we're going to start at 1. Now the Fibonacci sequence is very interesting. Fibonacci of Pisa, Leonardo of Pisa in Italy, called that as well. The way that it was created is very interesting. I'm not going to describe it in this video clip, but you might look it up and see how it's described in terms of how many fertile pairs of rabbits there are in each month if you start with a single pair of immature rabbits, and they reach maturity after 2 months. And in other words, they're fertile after 2 months and produce a new pair in the 3rd month. So the Fibonacci sequence then models that situation, and the equation itself is right here. Fn is equal to the sum of the previous 2 terms, Fn minus 1 and Fn minus 2, where this would apply when n is greater than or equal to 3. But we have to say what the first 2 terms are for this to make any sense at all. So we'll start with the first one being 1. F1 is 1 and F2 is 1. That would correspond to the 1 pair of rabbits in the 1st month, and that's all there is in the 2nd month. But now in the 3rd month they produce a pair, and so we'll see that in the 3rd month there'd be 2, right? The original pair plus a new pair. So again, just to write this out so it's all in one line, what this says is that a particular term in the sequence, the nth term, is the sum of the previous 2, the n minus first and n minus second terms. And so you can see how this would work out. So F2, oops, sorry, I got F3 would be f of 3 minus 1 is f sub 2 plus 3 minus 2 is 1. So that's f sub 1, that's just 1 plus 1 is 2. Like fashion, F4 is F3, 1 previous, and then 2 previous is F2, and F3 is 2, and F1 we were given, I'm sorry, F2 we were given up here, so that's 1, so we get 3. F4 we have then, so F5, sum of the previous 2 would be 3 plus 2 is 5. And if you continue this pattern on, you'll see that what you have is 1, 1, 2, 3, 5. And the next one would just be the sum of these 2. So we would get 8. And the next one would be the sum of these 2. So we get 13, and then 21, and then 34, and then 55, and so forth and so on, right? So there's the Fibonacci sequence. And what's remarkable about it, aside from a nice example of what is a recurrence relation, there's our recurrence relation. Let me write that first. What's remarkable about it is that it really does have some remarkable properties, one of which is that it occurs so frequently in nature. It is amazing, the different places where this occurs. Again, a Google search, a web search would show you some of the places where this occurs and some of the fascinating facts about it. I was just reading a book this year that had some basic history of mathematics, and it had something about the Fibonacci sequence I had never seen before, that dealt with just it being somehow optimal in some way, somehow the best in some way. Very interesting sequence. So let's talk about recurrence relations more generally, and I'm going to start with first order ones, but I think I'll save this for a second clip just to break this into usable pieces.